This is the third lecture in the introduction of enolates. As we said last lecture, the ketone, the carbonyl compounds exist in two different tautomers, and depending on how stable its tautomer is, it either exists mostly in the keto form, or in some cases it exists in enol form. All right. So the enols are also formed by catalysis of acid or base. So enols are much easily formed if you have a trace of acid or trace of base, as shown here. So I'm going to go over the formation of enols under acidic and basic conditions. This first one is under acidic condition, in which you have a carbonyl and you have acid catalyst around. And as you know, the first thing that's going to happen is the protonation to form the plus charge on this oxygen, which then makes it easier for the whatever nucleophile around to act as a base to remove this alpha proton. And when it does that, it's going to form the double bond between the two carbons, which will cause the oxygen double bond to break and be single bond to form the enol form. So this is a equilibrium process, so this could just as easily go back to this form and then go back to the ketone form. All right, and then notice when this proton is deprotonated, you are forming more of the acid, which is regenerated, and then it could go back with the keto form and make more of the enol form. All right. So under acid catalyst, enol is the only form that could form. Notice even in intermediate, you do not form enolate because you're doing this under acidic conditions where H plus is plenty. Under basic conditions, you have trace of base around, like a hydroxy anion, which will deprotonate the alpha proton, which will cause the C double bond C to occur, and then open up the double bond to form this enolate. And the enolate doesn't stay like that, but it will go and grab a proton, and notice the base is regenerated, and you form the enol. All right. So notice under basic conditions, enolate is the intermediate, and then by grabbing a proton, then you form the enol. All right. So the difference in formation of enol versus enolate is what base you're using. So notice in here the pKa of this ketone is around 20, and the pKa of the base that we're using is around 16. So the equilibrium is going to definitely exist, in which you have a mixture of the ketone, the mixture of the enol, all existing at the same time. All right. So if we want to just form the enolate and not form the enol, or have a mixture, a way to go about doing this is use of stronger base than the proton that you're removing. So if you go back to your first sheet where we talked about this, so if you use a weak base, so that's all in relative sense, right? So if the pKa of this is 20 and you're using a base that is lower in pKa, then that means it's not strong enough of a base. Then you're going to have an equilibrium occurring where you have a mixture of this as well as this. But if you use a base that is higher pKa than the proton that you're removing, then you should not have an equilibrium, but you have a irreversible reaction in which enolate forms, and then the enolate is there quantitatively, not as a mixture. So then this could go on and react with an electrophile. So that's the kind of condition that we're going to look at. So use a stronger base, meaning use base of higher pKa than the proton you're removing. All right. So one of the examples of the really strong base that's used often is a base called LDA. And LDA stands for lithium diisopropyl amide. So LDA. And it looks like this, where you have diisopropyl group, on the amine, and you have hydrogen. This would be diisopropyl amine, and you use a very strong base called n-butyllithium, which is even higher pKa than this. So the pKa of this is around 36, and the pKa of this is around 50. So this removes the proton, and in making this base called lithium. So lithium is a countercation diisopropyl amide, which you could buy, and this is a very strong base because it's around pKa of 36. And notice when we talked about the most of the ketones and alpha protons, they were in the range of 20 to 25. So this is strong enough to quantitatively remove the alpha proton. All right. So you will use this base to remove a typical alpha proton like acetone, and if you use LDA. And typically LDA is used at a minus 78 degrees in tetrahydrofuran, which is an inert solvent, and then you would have an enolate like this, in which you would not have an equilibrium, but you would have this enolate in place for it to then react with an electrophile. All right. So the byproduct of LDA is going back to the diisopropyl amine after it removes the alpha proton. All right. So what is the difference between enol and enolates, and which is more reactive, enolate or enol, and what conditions are used when forming each? You could probably now answer these questions, in which if you had a regular ketone or aldehyde or anything with the carbonyl where pKa is between around 20 to 25, and if you used sodium hydroxide or sodium ethoxide, these are pKa around 16. So what you're going to get is a mixture of and of course these are in water, so you're going to have a mixture of enolate with enol and the keto form. So you'll have a mixture of these intermediates because they're present in equilibrium. So the base that you're using is not strong enough to completely deprotonate. So whereas if you took this and you use LDA, then you would have complete enolization, and this is irreversible. So you would have enolate forming, not a mixture, and that way it's easy to now go and react with an electrophile and not have mixtures of compounds. All right, so what base should you choose depends on the pKa of the proton that you're deprotonating. All right, so if, for example, you were using let's say you were using diketone, in which you know that these protons, pKa of those are 9, then you don't need to use LDA, because this, I mean, that would be an overkill, right? Because these protons are low enough in pKa that you could actually use sodium methoxide, which has pKa of 16, and that would be strong enough to form enolate irreversibly. All right, so you have to look at each of these compounds that you are forming the enolate, and then decide which one is best for your that reaction. All right, so at this point you should be able to do 22.4, 22.5, and 22.6. As well as I forgot to mention up here 22.3. So basically 22.3 to 22.6 is what you should be able to do. And I'm not going to be able to finish this lecture, so I'm going to stop here and then finish up in the next lecture.